Solving general chemistry problems, thermodynamics. Here's a simple work problem. An ideal gas system operates against an external pressure of 5 bar. In so doing, the system performs 5 kilojoules of work on the surroundings. What is the change in volume of the system? Well, we've been taught that pressure-volume work is defined by the equation W equals minus P external delta V. As well, we've learned that when a system performs work on its surroundings, then we can conclude that it has used its internal energy to accomplish this work. Energy has left the system, and so the work is negative in sign. We can rearrange this equation to solve for delta V and get to the point where we have it equal to minus 5,000 joules divided by 5 bar. Recalling the relationship between the units of liter bar and joule as 100 joules equals 1 liter bar, we can use our unit algebra skills to solve this with good units and find that delta V equals 10 liters. Seems simple enough. Just remember your definitions and the unit conversion factors and all's good. But then you go ahead and look up the topic Work Thermodynamics on Wikipedia. In that article, it claims that the way this work is described, we should have identified it as being positive, not negative. As well, upon further reading, you find that they declare PV work to be given by the expression W equals plus P external delta V. Well, that makes two changes in sign, so the volume change answer is the same, but why the difference? Which approach is correct? Classical thermodynamics finds its roots in the Industrial Revolution, which was operating from the mid-1700s through to the middle of the 19th century. The main interest was to develop engines that would take heat from burning wood or coal and produce work. As scientists and both military and civil engineers came to understand the fundamentals, the concept of the internal energy of a system was born. That internal energy would increase when heat was added to the system, and the internal energy would decrease when work was taken out of it. This gave rise to the first law of thermodynamics, the idea of conservation of energy, and was given the mathematical form delta U equals Q minus W. As scientists developed a more theoretical understanding of the processes involved, the focus shifted from the utilitarian approach of heat in and work out to studying instead the system itself, rather than what the system can do, and viewing all positive energy flows, whether as heat or as work, as increasing the internal energy. The first law was altered to be delta U equals Q plus W. The difference between the two is simply how positive work is defined. To this day, the two versions of the first law are taught in the different disciplines. In science in general and in chemistry in particular, we will use the first law as delta U equals Q plus W, and work that injects energy into a system is positive. It might be worthwhile at this point to say a few words about heat and work. Heat is not so much energy, but rather it is a description of the flow of energy, the way in which energy is transferred. This can take a few forms. First, molecular collisions and interactions, along with radiation, and by radiation I mean light, think of an infrared heat lamp, are those most commonly viewed as giving rise to heat transfer in general chemistry. But friction is another form of heat transfer. Here the interface between the sledge and the floor is getting hotter as the friction injects energy into the internal energy of the interface. Closely related would be viscosity and also diffusion. These can all give rise to the flow of energy in the form of heat. Work is similarly best understood as a description of the flow of energy. It too can take many forms. Pressure volume or PV work arises from devices that involve the reciprocating changes in volume and pressure, principally effectuated by a piston. The other dominant form is called shaft work, involving a rotating shaft delivering power. Small power plants, such as the engine on a lawnmower or a car, employ an internal combustion engine that uses PV work to accomplish its task. Large power plants, such as coal, nuclear, or gas turbine, are all based on shaft power to transform their energy. Electrical work is increasing in importance, particularly for various green energy solutions. Batteries and fuel cells are beginning to replace internal combustion engines for transportation tasks. Solar energy via photovoltaics is another important converter source of electrical work. Other forms of work energy flow include spring, surface tension, magnetic, electrical polarization, and gravitational. In general chemistry, we tend to focus on PV work. There's a good reason for this. You'll run into a lot of discussions about pistons and use these devices to calculate PV work. The real reason that this is valuable, however, lies in the fact that so much chemistry takes place under conditions of constant pressure. Any time a reaction occurs in a beaker on the benchtop, any changes in gaseous components will introduce a need to consider the effects of volume changes against atmospheric pressure in order to understand its thermodynamics. So in chemistry, PV work is important, not just from the point of view of running an engine, but it gives us the framework to understand the role of work in chemical reactions. However, it is important to mention here that when we get to electrochemistry, we will find that electrical work is equally important in general chemistry.